184 Research Methodology 9 Testing of hypotheses. Parametric or standard tests of hypotheses. Hypothesis is usually considered as the principal instrument in research. Its main function is to suggest new experiments and observations. In fact, many experiments are carried out with the deliberate object of testing hypotheses. Decision makers often face situations wherein they are interested in testing hypotheses on the basis of available information and then take decisions on the basis of such testing. In social science, where direct knowledge of population parameters is rare, hypothesis testing is the often used strategy for deciding whether a sample data offers such support for a hypothesis that generalization can be made. Thus, hypothesis testing enables us to make probability statements about population parameters. The hypothesis may not be proved absolutely, but in practice it is accepted if it has withstood a critical testing. Before we explain how hypotheses are tested through different tests meant for the purpose, it will be appropriate to explain clearly the meaning of a hypothesis and the related concepts for better understanding of the hypothesis testing techniques. What is a hypothesis? Ordinarily, when one talks about hypothesis, one simply means a mere assumption or some supposition to be proved or disproved. But for a researcher, hypothesis is a formal question that he intends to resolve. Thus, a hypothesis may be defined as a proposition or a set of propositions set forth as an explanation for the occurrence of some specified group of phenomena, either asserted merely as a provisional conjecture to guide some investigation or accepted as highly probable in the light of established facts. Quite often, a research hypothesis is a predictive statement, capable of being tested by scientific methods, that relates an independent variable to some dependent variable. For example, consider statements like the following ones. Students who receive counseling will show a greater increase in creativity than students not receiving counseling, or, the automobile A is performing as well as automobile B. These are hypotheses capable of being objectively verified and tested. Thus, we may conclude that a hypothesis states what we are looking for, and it is a proposition which can be put to a test to determine its validity. Testing of hypotheses. 185 Characteristics of hypothesis. Hypothesis must possess the following characteristics. Hypothesis should be clear and precise. If the hypothesis is not clear and precise, the inferences drawn on its basis cannot be taken as reliable. Hypothesis should be capable of being tested. In a swamp of untestable hypotheses, many a time the research programs have bogged down. Some prior study may be done by researcher in order to make hypothesis a testable one. A hypothesis is testable if other deductions can be made from it which, in turn, can be confirmed or disproved by observation. 1. Hypothesis should state relationship between variables if it happens to be a relational hypothesis. Hypothesis should be limited in scope and must be specific. A researcher must remember that narrower hypotheses are generally more testable, and he should develop such hypotheses. Hypothesis should be stated as far as possible in most simple terms so that the same is easily understandable by all concerned. But one must remember that simplicity of hypothesis has nothing to do with its significance. Hypothesis should be consistent with most known facts, i.e., it must be consistent with a substantial body of established facts. In other words, it should be one which judges accept as being the most likely. Hypothesis should be amenable to testing within a reasonable time. One should not use even an excellent hypothesis if the same cannot be tested in reasonable time, for one cannot spend a lifetime collecting data to test it. Hypothesis must explain the facts that gave rise to the need for explanation. This means that by using the hypothesis plus other known and accepted generalizations, one should be able to deduce the original problem condition. Thus, hypothesis must actually explain what it claims to explain. It should have empirical reference. Basic concepts concerning testing of hypotheses. Basic concepts in the context of testing of hypotheses need to be explained. A null hypothesis and alternative hypothesis. In the context of statistical analysis, we often talk about null hypothesis and alternative hypothesis. If we are to compare method A with method B about its superiority, and if we proceed on the assumption that both methods are equally good, then this assumption is termed as the null hypothesis. As against this, we may think that the method A is superior or the method B is inferior. We are then stating what is termed as alternative hypothesis. The null hypothesis is generally symbolized as H0 and the alternative hypothesis is HA. Suppose we want to test the hypothesis that the population mean μBg is equal to the hypothesized mean μH0di equals 100. Then we would say that the null hypothesis is that the population mean is equal to the hypothesized mean 100, and symbolically we can express as H0 micro equals HO 100 1c. William Emery, Business Research Methods, p. 33. 186 Research methodology. If our sample results do not support this null hypothesis, we should conclude that something else is true. What we conclude rejecting the null hypothesis is known as alternative hypothesis. In other words, the set of alternatives to the null hypothesis is referred to as the alternative hypothesis. If we H accept H0, then we are rejecting HA, and if we reject H0, then we are accepting HA. For H0, micro 100, we may consider three possible alternative hypotheses as follows. 0 alternative hypothesis. Micro Ha H does not equal 0. Table 9.1 to be read as follows. The alternative hypothesis is that the population mean is not equal to 100, i.e., it may be more or less than 100. Micro Ha H greater than 0. Micro Ha H. The alternative hypothesis is that the population mean is greater than 100, less than 0. The alternative hypothesis is that the population mean is less than 100. The null hypothesis and the alternative hypothesis are chosen before the sample is drawn. The researcher must avoid the error of deriving hypotheses from the data that he collects and then testing the hypotheses from the same data. In the choice of null hypothesis, the following considerations are usually kept in view. A alternative hypothesis is usually the one which one wishes to prove, and the null hypothesis is the one which one wishes to disprove. Thus, a null hypothesis represents the hypothesis we are trying to reject, and alternative hypothesis represents all other possibilities. B. If the rejection of a certain hypothesis when it is actually true involves great risk, it is taken as null hypothesis because then the probability of rejecting it when it is true is alpha, the level of significance which is chosen very small. C. Null hypothesis should always be specific hypothesis, i.e., it should not state about or approximately a certain value. Generally, in hypothesis testing we proceed on the basis of null hypothesis, keeping the alternative hypothesis in view. Why so? The answer is that on the assumption that null hypothesis is true, one can assign the probabilities to different possible sample results, but this cannot be done if we proceed with the alternative hypothesis. Hence the use of null hypothesis, at times also known as statistical hypothesis, is quite frequent. B. The level of significance. This is a very important concept in the context of hypothesis testing. It is always some percentage, usually 5%, which should be chosen with great care, thought and reason. In case we take the significance level at 5%, then this implies that H0 will be rejected if a hypothesis is of the type micro or equals H0, then we call such a hypothesis a simple or specific hypothesis, but if it is of the type micro does not equal greater than less than or HHH, then we call it a composite or nonspecific hypothesis. 000. Testing of hypotheses. I-187 when the sampling result, i.e., observed evidence, has a less than 0.05 probability of occurring if H0 is true. In other words, the 5% level of significance means that researcher is willing to take as much as a 5% risk of rejecting the null hypothesis when it, H0, happens to be true. Thus the significance level is the maximum value of the probability of rejecting H0 when it is true and is usually determined in advance before testing the hypothesis. See decision rule or test of hypothesis. Given a hypothesis H0 and an alternative hypothesis HA, we make a rule which is known as decision rule, according to which we accept H0, i.e., reject HA, or reject H0, i.e., accept HA. For instance, if H0 is that a certain lot is good, there are very few defective items in it, against HA, that the lot is not good, there are too many defective items in it. Then we must decide the number of items to be tested and the criterion for accepting or rejecting the hypothesis. We might test 10 items in the lot and plan our decision saying that if there are none or only one defective item among the 10, we will accept H0, otherwise we will reject H0 or accept HA. This sort of basis is known as decision rule. D. Type 1 and Type 2 errors. In the context of testing of hypotheses, there are basically two types of errors we can make. We may reject H0 when H0 is true, and we may accept H0 when in fact H0 is not true. The former is known as Type 1 error and the latter is Type 2 error. In other words, Type 1 error means rejection of hypothesis which should have been accepted, and Type 2 error means accepting the hypothesis which should have been rejected. Type 1 error is denoted by alpha, known as alpha error, also called the level of significance of test, and Type 2 error is denoted by beta, known as beta error. In a tabular form the said two errors can be presented as follows. Table 9.2 Decision accept H0 H0 true H0 false correct decision type 2 error beta error reject H0 type 1 error alpha error correct decision. The probability of type 1 error is usually determined in advance and is understood as the level of significance of testing the hypothesis. If type 1 error is fixed at 5%, it means that there are about 5 chances in 100 that we will reject H0 when H0 is true. We can control type 1 error just by fixing it at a lower level. For instance, if we fix it at 1%, we will say that the maximum probability of committing type 1 error would only be 0.01. But with a fixed sample size, n, when we try to reduce type 1 error, the probability of committing type 2 error increases. Both types of errors cannot be reduced simultaneously. There is a trade-off between two types of errors, which means that the probability of making one type of error can only be reduced if we are willing to increase the probability of making the other type of error. To deal with this trade-off in business situations, decision makers decide the appropriate level of type 1 error by examining the costs or penalties attached to both types of errors. If type 1 error involves the time and trouble of reworking a batch of chemicals that should have been accepted, whereas type 2 error means taking a chance that an entire group of users of this chemical compound will be poisoned, then 188 Research methodology. In such a situation, one should prefer a type 1 error to a type 2 error. As a result, one must set very high level for type 1 error in one's testing technique of a given hypothesis. Point 2 Hence, in the testing of hypothesis, one must make all possible effort to strike an adequate balance between type 1 and type 2 errors. Two-tailed and one-tailed tests. In the context of hypothesis testing, these two terms are quite important and must be clearly understood. A two-tailed test rejects the null hypothesis if, say, the sample mean is significantly higher or lower than the hypothesized value of the mean of the population. Such a test is appropriate when the null hypothesis is some specified value and the alternative hypothesis is a value not equal to the specified value of the null hypothesis. Symbolically, the two-tailed test is appropriate when we have H0 or micro H equals and ha H0. Micro does not equal 0, which may mean micro greater than H0, less than H0. Thus, in a two-tailed test, there are two rejection regions, one on each tail of the curve, which can be illustrated as under. Acceptance and rejection regions. In case of a two-tailed test with 5% significance level, rejection region limit acceptance region, accept H0 if the sample mean falls in this region by 0.475 of area, limit rejection region 0.475 of area, 0.025 of area, both taken together equals 0.95 or 95% of area, z equals minus 1.96, reject xmm H0 equals H0 if the sample mean falls in either of these two regions. Fig. 9.12 Richard I. Levin, Statistics for Management, p. 247-248. Also known as critical regions. 0.025 of area, z equals 1.96. Testing of hypotheses. I-189 Mathematically we can state, acceptance region AZ, less than 196, rejection region RZ, greater than 196. If the significance level is 5% and the two-tailed test is to be applied, the probability of the rejection area will be 0.05, equally splitted on both tails of the curve is 0.025, and that of the acceptance region will be 0.95 as shown in the above curve. If we take micro equals 100 and if our sample mean deviates significantly from 100 in either direction, then we shall reject the null hypothesis, but if the sample mean does not deviate significantly from micro, in that case we shall accept the null hypothesis. But there are situations when only one-tailed test is considered appropriate. A one-tailed test would be used when we are to test, say, whether the population mean is either lower than or higher than some hypothesized value. For instance, if RH0, micro H equals and ha H0, micro less than 0, then we are interested in what is known as left-tailed test, wherein there is one rejection region only on the left tail, which can be illustrated as below. Acceptance and rejection regions. In case of one-tailed test, left tail with 5% significance, rejection region, limit acceptance region, accept H0 if the sample mean falls in this region, 0.45 of area, 0.50 of area, 0.05 of area, both taken together equals 0.95 or 95% of area, z equals minus 1.645, reject Hx0 if the sample mean falls in this region, mmH equals 0. Fig. 9.2 Mathematically we can state, acceptance region AZ, greater than minus 1645, rejection region RZ, less than minus 1645. 190 Research methodology. If R micro equals 100 and if our sample mean deviates significantly from 100 in the lower direction, we shall reject H0, otherwise we shall accept H0 at a certain level of significance. If the significance level in the given case is kept at 5%, then the rejection region will be equal to 0.05 of area in the left tail as has been shown in the above curve. In case R H0, micro H equals and Ha H0, micro greater than 0, we are then interested in what is known as one-tailed test right tail, and the rejection region will be on the right tail of the curve as shown below. Acceptance and rejection regions. In case of one-tailed test right tail with 5% significance level, acceptance region, accept H0 if the sample mean falls in this region, rejection region limit 0.05 of area, 0.45 of area both taken together equals 0.95 or 95% of area, H0 equals 0.05 of area, Z equals minus 1.645, reject H0 if the sample mean falls in this region. Fig. 9.3. Mathematically we can state acceptance region AZ less than 1645. Rejection region AZ greater than 1645. If R micro equals 100 and if our sample mean deviates significantly from 100 in the upward direction, we shall reject H0, otherwise we shall accept the same. If in the given case the significance level is kept at 5%, then the rejection region will be equal to 0.05 of area in the right tail as has been shown in the above curve. It should always be remembered that accepting H0 on the basis of sample information does not constitute the proof that H0 is true. We only mean that there is no statistical evidence to reject it, but we are certainly not saying that H0 is true, although we behave as if H0 is true. Testing of hypotheses. I-191 Procedure for hypothesis testing. To test a hypothesis means to tell, on the basis of the data the researcher has collected, whether or not the hypothesis seems to be valid. In hypothesis testing, the main question is whether to accept the null hypothesis or not to accept the null hypothesis. Procedure for hypothesis testing refers to all those steps that we undertake for making a choice between the two actions, i.e., rejection and acceptance of a null hypothesis. The various steps involved in hypothesis testing are stated below. Making a formal statement. The step consists in making a formal statement of the null hypothesis H0 and also of the alternative hypothesis Ha. This means that hypotheses should be clearly stated. Considering the nature of the research problem. For instance, Mr. Mohan of the Civil Engineering Department wants to test the load-bearing capacity of an old bridge which must be more than 10 tons. In that case he can state his hypotheses as under. Null hypothesis H0, T micro equals 10 on S. Alternative hypothesis Ha, T micro greater than 10 on S. Take another example. The average score in an aptitude test administered at the national level is 80. To evaluate a state's education system, the average score of 100 of the state's students selected on random basis was 75. The state wants to know if there is a significant difference between the local scores and the national scores. In such a situation the hypotheses may be stated as under. Null hypothesis H0, 8 micro equals 0. Alternative hypothesis Ha, 8 micro does not equal 0. The formulation of hypotheses is an important step which must be accomplished with due care in accordance with the object and nature of the problem under consideration. It also indicates whether we should use a one-tailed test or a two-tailed test. If Ha is of the type greater than or of the type lesser than, we use a one-tailed test, but when Ha is of the type, whether greater or smaller, then we use a two-tailed test. Selecting a significance level. The hypotheses are tested on a predetermined level of significance and as such the same should be specified. Generally, in practice, either 5% level or 1% level is adopted for the purpose. The factors that affect the level of significance are a. The magnitude of the difference between sample means, b. The size of the samples, c. The variability of measurements within samples, and d. Whether the hypothesis is directional or non-directional. A directional hypothesis is one which predicts the direction of the difference between, say, means. In brief, the level of significance must be adequate in the context of the purpose and nature of enquiry. Deciding the distribution to use. After deciding the level of significance, the next step in hypothesis testing is to determine the appropriate sampling distribution. The choice generally remains between normal distribution and the t-distribution. The rules for selecting the correct distribution are similar to those which we have stated earlier in the context of estimation. Selecting a random sample and computing an appropriate value. Another step is to select a random samples and compute an appropriate value from the sample data concerning the test statistic utilizing the relevant distribution. In other words, draw a sample to furnish empirical data. v. Calculation of the probability. One has then to calculate the probability that the sample result would diverge as widely as it has from expectations, if the null hypothesis were in fact true. 192 Research methodology v. Comparing the probability. Yet another step consists in comparing the probability thus calculated with the specified value for alpha, the significance level. If the calculated probability is equal to or smaller than the alpha value in case of one-tailed test, and alpha 2 in case of two-tailed test, then reject the null hypothesis, i.e., accept the alternative hypothesis, but if the calculated probability is greater, then accept the null hypothesis. In case we reject H0, we run a risk of, at most, the level of significance committing an error of type 1, but if we accept H0, then we run some risk, the size of which cannot be specified as long as the H0 happens to be vague rather than specific, of committing an error of type 2. Flow diagram for hypothesis testing. The above stated general procedure for hypothesis testing can also be depicted in the form of a flowchart for better understanding as shown in Fig. 9.4. Free flow diagram for hypothesisting state as well as HH0A. Specify the level of significance, or the value, decide the correct sampling distribution, sample a random samples and work out an appropriate value from sample data. Calculate the probability that sample result would diverge as widely as it has from expectations. If H0 were true, is this probability equal to or smaller than value in case of one-tailed test and 2 in case of two-tailed test? Yes. Reject H0, thereby run the risk of committing type 1 error. No. Accept H0, thereby run some risk of committing type 2 error. Fig. 9.43 Based on the flow diagram in William A. Chance's Statistical Methods for Decision Making, Richard D. Irwin Inc., Illinois, 1969, page .48. Testing of hypotheses. I-193 Measuring the power of a hypothesis test. As stated above, we may commit type 1 and type 2 errors while testing a hypothesis. The probability of type 1 error is denoted as alpha, the significance level of the test, and the probability of type 2 error is referred to as beta. Usually the significance level of a test is assigned in advance, and once we decide it, there is nothing else we can do about alpha. But what can we say about beta? We all know that hypothesis test cannot be foolproof. Sometimes the test does not reject H0 when it happens to be a false one, and this way a type 2 error is made. But we would certainly like that beta, the probability of accepting H0 when H0 is not true, to be as small as possible. Alternatively, we would like that 1 beta, the probability of rejecting H0 when H0 is not true, to be as large as possible. If 1 beta is very much nearer to unity, i.e., nearer to 1.0, we can infer that the test is working quite well, meaning thereby that the test is rejecting H0 when it is not true, and if 1 beta is very much nearer to 0.0, then we infer that the test is poorly working, meaning thereby that it is not rejecting H0 when H0 is not true. Accordingly, 1 beta value is the measure of how well the test is working, or what is technically described as the power of the test. In case we plot the values of 1 beta for each possible value of the population parameter, say micro, the true population mean, for which the H0 is not true, alternatively the HA is true, the resulting curve is known as the power curve associated with the given test. Thus, power curve of a hypothesis test is the curve that shows the conditional probability of rejecting H0 as a function of the population parameter and size of the sample. The function defining this curve is known as the power function. In other words, the power function of a test is that function defined for all values of the parameters which yields the probability that H0 is rejected, and the value of the power function at a specific parameter point is called the power of the test at that point. As the population parameter gets closer and closer to hypothesized value of the population parameter, the power of the test, i.e., 1 beta, must get closer and closer to the probability of rejecting H0 when the population parameter is exactly equal to hypothesized value of the parameter. We know that this probability is simply the significance level of the test, and as such the power curve of a test terminates at a point that lies at a height of alpha, the significance level, directly over the population parameter. Closely related to the power function, there is another function which is known as the operating characteristic function, which shows the conditional probability of accepting H0 for all values of population parameters for a given sample size, whether or not the decision happens to be a correct one. If power function is represented as H and operating characteristic function is L, then we have L equals 1H. However, one needs only one of these two functions for any decision rule in the context of testing hypotheses. How to compute the power of a test, i.e., 1 beta, can be explained through examples. Illustration 1. A certain chemical process is said to have produced 15 or less pounds of waste material for every 60 pounds, batch with a corresponding standard deviation of 5 pounds. A random sample of 100 batches gives an average of 16 pounds of waste per batch. Test at 10% level whether the average quantity of waste per batch has increased. Compute the power of the test for micro equals 16 pounds. If we raise the level of significance to 20%, then how the power of the test for micro equals 16 pounds would be affected. 194 Research Methodology Solution. As we want to test the hypothesis that the average quantity of waste per batch of 60 pounds is 15 or less pounds against the hypothesis that the waste quantity is more than 15 pounds, we can write as under: H0H, micro less than 15 pounds. A. LBS, micro greater than 15 as Ha is one-sided. We shall use the one-tailed test in the right tail because Ha is of more than type at 10% level for finding the value of standard deviate Z corresponding to 0.4000 area of normal curve, which comes to 1.28 as per normal curve area table. From this we can find the limit of micro for accepting H0 as under, exceptor if O15128HXNP less than plus alpha x less than plus 151285100, EJ or x less than 1564, a 10% level of significance otherwise except Ha. But the sample average is 16 pounds, which does not come in the acceptance region as above. We, therefore, reject H0 and conclude that average quantity of waste per batch has increased. For finding the power of the test, we first calculate beta and then subtract it from 1. Since beta is a conditional probability which depends on the value of micro, we take it as 16 as given in the question. We can now write beta equals P except H01516 micro if x less than 1564. Less than equals. Since we have already worked out that H0 is accepted at 10% level of significance, therefore Px 1564 equals less than equals beta micro 16, which can be depicted as follows: acceptance region rejection region 1b equals Bg 07642b equals 02358. X equals 1564. M equals 16 fig. 9.5 asterisk table no. 1. Given in appendix at the end of the book. Testing of hypotheses I-195. We can find out the probability of the area that lies between 15.64 and 16 in the above curve first by finding Z and then using the area table for the purpose. In the given case equals minus ZXN micro sigma equals minus 1564 165 100 072. Corresponding to which the area is 0.2642. Hence, beta equals 0.5000.2642 equals 0.2358 and the power of the test equals 1 beta equals 1.2358 equals 0.7642 for micro equals 16. In case the significance level is raised to 20%, then we shall have the following criteria, except if HXO 15845 100 less than plus BGEJ or X less than 1542. Otherwise except Ha therefore equals less than equals Px 1542 16. Beta micro DI or beta equals 1230 using normal curve area table as explained above. Hence, 1 beta BG minus equals 1 1230 8770. Tests of hypotheses. As has been stated above, that hypothesis testing determines the validity of the assumption technically described as null hypothesis with a view to choose between two conflicting hypotheses about the value of a population parameter. Hypothesis testing helps to decide on the basis of a sample data whether a hypothesis about the population is likely to be true or false. Statisticians have developed several tests of hypotheses, also known as the tests of significance, for the purpose of testing of hypotheses, which can be classified as A. Parametric tests or standard tests of hypotheses, and B. Non-parametric tests or distribution-free test of hypotheses. Parametric tests usually assume certain properties of the parent population from which we draw samples. Assumptions like observations come from a normal population, sample size is large, assumptions about the population parameters like mean, variance, etc., must hold good before parametric tests can be used. But there are situations when the researcher cannot or does not want to make such assumptions. In such situations we use statistical methods for testing hypotheses, which are called non-parametric tests because such tests do not depend on any assumption about the parameters of the parent population. Besides, most non-parametric tests assume only nominal or ordinal data, whereas parametric tests require measurement equivalent to at least an interval scale. As a result, non-parametric tests need more observations than parametric tests to achieve the same size of type 1 and type 2 errors. Point 4. We take up in the present chapter some of the important parametric tests, whereas non-parametric tests will be dealt with in a separate chapter later in the book. Important parametric tests. The important parametric tests are 1. Z-test, 2. T-test, *3 Chi-2 test, and 4. F-test. All these tests are based on the assumption of normality, i.e., the source of data is considered to be normally distributed. 4. Donald L. Harnett and James L. Murphy, Introductory Statistical Analysis, p. 368. Chi-2 test is also used as a test of goodness of fit and also as a test of independence, in which case it is a non-parametric test. This has been made clear in Chapter 10 entitled Chi-2 test. 196. Research methodology. In some cases the population may not be normally distributed, yet the tests will be applicable on account of the fact that we mostly deal with samples and the sampling distributions closely approach normal distributions. Z-test is based on the normal probability distribution and is used for judging the significance of several statistical measures, particularly the mean. The relevant test statistic, Z, is worked out and compared with its probable value, to be read from tables showing area under normal curve, at a specified level of significance for judging the significance of the measure concerned. This is a most frequently used test in research studies. This test is used even when binomial distribution or t-distribution is applicable on the presumption that such a distribution tends to approximate normal distribution as n becomes larger. Z-test is generally used for comparing the mean of a sample to some hypothesized mean for the population in case of large sample, or when population variance is known. Z-test is also used for judging the significance of difference between means of two independent samples in case of large samples, or when population variance is known. Z-test is also used for comparing the sample proportion to a theoretical value of population proportion or for judging the difference in proportions of two independent samples when n happens to be large. Besides, this test may be used for judging the significance of median, mode, coefficient of correlation and several other measures. T-test is based on t-distribution and is considered an appropriate test for judging the significance of a sample mean or for judging the significance of difference between the means of two samples in case of small samples when population variance is not known, in which case we use variance of the sample as an estimate of the population variance. In case two samples are related, we use paired t-test, or what is known as difference test, for judging the significance of the mean of difference between the two related samples. It can also be used for judging the significance of the coefficients of simple and partial correlations. The relevant test statistic, t, is calculated from the sample data and then compared with its probable value based on t-distribution, to be read from the table that gives probable values of t for different levels of significance for different degrees of freedom, at a specified level of significance for concerning degrees of freedom for accepting or rejecting the null hypothesis. It may be noted that t-test applies only in case of small samples when population variance is unknown. Chi-2 test is based on chi-square distribution and as a parametric test is used for comparing a sample variance to a theoretical population variance. F-test is based on F distribution and is used to compare the variance of the two independent samples. This test is also used in the context of analysis of variance ANOVA for judging the significance of more than two sample means at one and the same time. It is also used for judging the significance of multiple correlation coefficients. Test statistic, F, is calculated and compared with its probable value, to be seen in the F ratio tables for different degrees of freedom for greater and smaller variances at specified level of significance for accepting or rejecting the null hypothesis. The table on pages 198 to 201 summarizes the important parametric tests along with test statistics and test situations for testing hypotheses relating to important parameters often used in research studies in the context of one sample and also in the context of two samples. We can now explain and illustrate the use of the above-stated test statistics in testing of hypotheses. The test statistic is the value obtained from the sample data that corresponds to the parameter under investigation. Testing of hypotheses. I-197 hypothesis testing of mean of the population can be tested presuming different situations such as the population may be normal or other than normal, it may be finite or infinite, sample size may be large or small, variance of the population may be known or unknown and the alternative hypothesis may be two-sided or one-sided. Our testing technique will differ in different situations. We may consider some of the important situations. 1. Population normal, population infinite, sample size may be large or small but variance of the population is known, Ha may be one-sided or two-sided, In such a situation, z-test is used for testing hypothesis of mean and the test statistic z is worked r as under zx equals minus micro sigma pnh0. 2. Population normal, population finite, sample size may be large or small but variance of the population is known, ha may be one-sided or two-sided. In such a situation, z-test is used and the test statistic z is worked out as under using finite population multiplier x z micro equals minus times minus h sigma 0 PEJBGBGNNNN minus 1 3. Population normal, population infinite, sample size small and variance of the population unknown, ha may be one-sided or two-sided. In such a situation, t-test is used and the test statistic t is worked out as under xt and equals minus micro sigma s nh0 with d f equals n1 2 sigma s xx equals n airy summation minus dinbg 4. Population normal, population finite, sample size small and variance of the population unknown, and ha may be one-sided or two-sided. In such a situation, t-test is used and the test statistic t is worked out as under using finite population multiplier xt micro equals minus times minus h sigma 0 EJBGBG with d f equals n1 SNNNN minus 1. 198 Research Methodology Table 9.3. Names of some parametric tests along with test situations and test statistics used in context of hypothesis testing. Unknown test situation, population name of the test and the test statistic to be used, parameter characteristics and other conditions. Random 1 sample 2 samples. Sampling is assumed in all situations along with independent related infinite population 1 2 3 4 5 mean, micropopulations normal or z-test and the z-test for difference in means and the test sample size large, i.e. test statistic n greater than 30 or population variances known zxnhp equals minus micro sigma 0 zxxnnp equals minus plus fhgikj 1221211 sigma. In case sigma p is not is used when two samples are drawn from the known, we use same population. In case sigma p is not known, we use sigma s in its place, sigma s12 in its place. Calculating sigma s xxn equals minus sigma di21 sigma sssndndnn 1 2 1 1 2 1 2 2 2 2 2 2 1 2 equals plus ej where dxx1 1 1 2 equals minus didxx2 2 1 2 equals minus dixnxnxnn 1 2 1 1 2 2 1 2 equals plus counted. Testing of hypotheses I-199 1 2 3 4 5 ORZXXNNPP 1 2 1 2 1 2 2 2 minus plus sigma is used when two samples are drawn from different populations. In case sigma P1 and sigma P2 are not known, we use sigma SS1 2 and respectively in their places. Calculating sigma SXXN1 1 1 2 1 1 equals minus sigma di and sigma SIXXN2 2 2 2 2 1 equals minus sigma di mean, micropopulations normal t-test and the t-test for difference in means and the test statistic paired t-test or and test statistic difference test and sample size small, i.e. the test statistic n less than 30 txnhs equals minus micro sigma 0 txxxxxxnnnnii equals minus plus times plus 1 2 1 1 2 2 2 2 1 2 1 2 2 1 1 sigma diddddnnni equals minus 0 1 2 2 sigma, with d f equals n1 plus n2 to 2 with d f equals n1 d f equals n1 where n equals number of where counted. And population variance is unknown but the population variance is assumed equal in case of test on difference between means. 200 Research Methodology 1 2 3 4 5 sigma s6xn equals minus sigma di2 1 pairs in two samples. Alternatively, t can be worked out as under xxnnnnnnnnndxyssiii 1 2 1 1 2 2 2 2 1 2 1 2 1 2 1 1 2 1 1 2 minus plus times plus equals plus minus rst uvw equals minus bg sigma with d f differences, i.e. proportion repeated independent z-test and the z-test for difference in proportions of 2p trials, sample size test statistic samples and the test statistic large presuming normal approximation of binomial zppqn equals minus dot operator dollar zppqnpqn equals minus plus dollar $121112222 distribution if p and q are as used in case of heterogeneous populations. But not known, when populations are similar with respect to a then we use given attribute, we work out the best estimate of p and q in there the population proportion as under Places PNPNPNN011212 equals plus plus dollar counted. Testing of hypotheses I201, 1, 2, 3, 4, 5 and QP001 equals minus, in which case we calculate test statistic ZPPPQNN equals minus plus FHGIKJ $12001211 variance populations Chi2 test and the test F test and the test statistic sigma P2EJ normal. Observations statistic FXXNXXNSSII equals N Airy summation minus N Airy summation minus sigma 1 2 2 2 1 1 2 2 2 2 1 1 DI are independent chi sigma 2 2 2 1 equals minus SPNBG, where sigma S12 is treated greater than sigma S22 with D. F equals N1 with D. F equals version 1 equals N1 minus 1 for greater variance, and D. F equals version 2 equals N2 to 1 for smaller variance. In the table the various symbols stand as under. X equals mean of the sample, X1 equals mean of sample 1, X2 equals mean of sample 2, N equals no of items in a sample, N1 equals no of items in sample 1, N2 equals no of items in sample 2, micro H0 equals hypothesized mean for population, sigma P equals standard deviation of population, sigma S equals standard deviation of sample, P equals population proportion, QPP equals minus 1, dollar equals sample proportion, dollar QP equals minus 1. 202 Research methodology and sigma SXXN equals N Airy summation minus DIBG2 1 5. Population may not be normal but sample size is large, variance of the population may be known or unknown, and HA may be one-sided or two-sided. In such a situation we use z-test and work out the test statistic z as under. ZXNHP equals minus micro sigma 0. This applies in case of infinite population when variance of the population is known, but when variance is not known, we use sigma S in place of sigma P in this formula. ORZXNNNNHP equals minus times minus micro sigma 01 EJBGBG. This applies in case of finite population when variance of the population is known, but when variance is not known, we use sigma S in place of sigma P in this formula. Illustration 2. A sample of 400 male students is found to have a mean height 67.47 inches. Can it be reasonably regarded as a sample from a large population with mean height 67.39 inches and standard deviation 1.30 inches? Test at 5% level of significance. Solution. Taking the null hypothesis that the mean height of the population is equal to 67.39 inches, we can write HHO 6739 micro equals HH micro 06739 does not equal, and the given information is XP equals 6747130. Sigma N equals 400. Assuming the population to be normal, we can work out the test statistic Z as under. ZXNHP equals micro sigma 0, 6747 6739 130 400 008 0065 1231. /. As HA is two-sided in the given question, we shall be applying a two-tailed test for determining the rejection regions at 5% level of significance, which comes to as under. Using normal curve area table, R, Z greater than 1.96, the observed value of Z is 1.231, which is in the acceptance region since R, Z greater than 1.96 and thus H0 is accepted. We may conclude that the given sample with mean height equals 67.47 can be regarded. Testing of hypotheses I203 to have been taken from a population with mean height 67.39 and standard deviation 1.30 at 5% level of significance. Illustration 3. Suppose we are interested in a population of 20 industrial units of the same size, all of which are experiencing excessive labor turnover problems. The past records show that the mean of the distribution of annual turnover is 320 employees, with a standard deviation of 75 employees. A sample of 5 of these industrial units is taken at random, which gives a mean of annual turnover is 300 employees. Is the sample mean consistent with the population mean? Test at 5% level. Solution. Taking the null hypothesis that the population mean is 320 employees, we can write HHO 320. Employees micro equals HH. Employees micro 0320 does not equal in the given information as under. X equals 300 employees, sigma P equals 75 employees, N equals 5, N equals 20. Assuming the population to be normal, we can work out the test statistic Z as under. ZXNNNHP 202 Research methodology and sigma S6xn equals n Airy summation minus DIBG2 15. Population may not be normal but sample size is large, variance of the population may be known or unknown, and Ha may be one-sided or two-sided. In such a situation we use z-test and work out the test statistic z as under. Zxnhp equals minus micro sigma 0. This applies in case of infinite population when variance of the population is known but when variance is not known, we use sigma s in place of sigma p in this formula. ORZXNNNHP equals minus times minus micro sigma 01 EJBGBG. This applies in case of finite population when variance of the population is known but when variance is not known, we use sigma s in place of sigma p in this formula. Illustration 2. A sample of 400 male students is found to have a mean height 67.47 inches. Can it be reasonably regarded as a sample from a large population with mean height 67.39 inches and standard deviation 1.30 inches? Test at 5% level of significance. Solution. Taking the null hypothesis that the mean height of the population is equal to 67.39 inches, we can write HHOO 6739 micro equals Ha h micro 06739 does not equal, and the given information is xp equals 6747130. Sigma n equals 400. Assuming the population to be normal, we can work out the test statistic z as under. Zxnhp equals micro sigma 0, 6747 6739 130 400 008 0065 1231. As Ha is two-sided in the given question, we shall be applying a two-tailed test for determining the rejection regions at 5% level of significance, which comes to as under, using normal curve area table. R, z greater than 1.96. The observed value of z is 1.231, which is in the acceptance region since R, z greater than 1.96 and thus h0 is accepted. We may conclude that the given sample with mean height equals 67.47 can be regarded. Testing of hypotheses I203 to have been taken from a population with mean height 67.39 and standard deviation 1.30 at 5% level of significance. Illustration 3. Suppose we are interested in a population of 20 industrial units of the same size, all of which are experiencing excessive labor turnover problems. The past records show that the mean of the distribution of annual turnover is 320 employees, with a standard deviation of 75 employees. A sample of 5 of these industrial units is taken at random, which gives a mean of annual turnover is 300 employees. Is the sample mean consistent with the population mean? Test at 5% level. Solution. Taking the null hypothesis that the population mean is 320 employees, we can write HHOO 320. Employees micro equals Ha h. Employees micro 0320 does not equal, and the given information as under. X equals 300 employees, sigma p equals 75 employees, n equals 5, n equals 20. Assuming the population to be normal, we can work out the test statistic z as under. Zxnnnnhp equals minus times minus micro sigma 01 bgbg equals minus times minus equals minus 300 320 75520 520 120 3354 888 bgbg equals 0.67. As Ha is two-sided in the given question, we shall apply a two-tailed test for determining the rejection regions at 5% level of significance, which comes to as under, using normal curve area table. R, z greater than 1.96. The observed value of z is minus 0.67, which is in the acceptance region since R, z greater than 1.96, and thus, h0 is accepted, and we may conclude that the sample mean is consistent with population mean, i.e., the population mean 320 is supported by sample results. Illustration 4. The mean of a certain production process is known to be 50 with a standard deviation of 2.5. The production manager may welcome any change as mean value towards higher side but would like to safeguard against decreasing values of mean. He takes a sample of 12 items that gives a mean value of 48.5. What inference should the manager take for the production process on the basis of sample results? Use 5% level of significance for the purpose. Solution. Taking the mean value of the population to be 50, we may write HHOO 50 micro equals being a case of finite population. 204 Research methodology. Ha h micro 050 less than, since the manager wants to safeguard against decreasing values of mean, and the given information is xp equals 485.25, sigma and n equals 12. Assuming the population to be normal, we can work out the test statistic z as under zxnhp equals minus micro sigma o 485502512152534642078 slash dot dot. BGBG is Ha is one-sided in the given question. We shall determine the rejection region applying one-tailed test in the left tail because Ha is of less than type at 5% level of significance, and it comes to as under, using normal curve area table, R, z less than 1.645. The observed value of z is 2.0784, which is in the rejection region, and thus, H0 is rejected at 5% level of significance. We can conclude that the production process is showing mean which is significantly less than the population mean, and this calls for some corrective action concerning the said process. Illustration 5. The specimen of copper wires drawn form a large lot have the following breaking strength in kilogram weight: 578, 572, 570, 568, 572, 578, 570, 572, 596, 544. Test using student's T statistic whether the mean breaking strength of the lot may be taken to be 578 kg weight. Test at 5% level of significance. Verify the inference so drawn by using Sandler's A statistic as well. Solution. Taking the null hypothesis that the population mean is equal to hypothesized mean of 578 kg, we can write HHOO 578 kg micro equals Ha H micro does not equal 0 as the sample size is small since n equals 10 and the population standard deviation is not known. We shall use t-test assuming normal population and shall work out the test statistic t as under txnhs equals minus micro sigma 0. To find x and sigma s we make the following computations. S. No. She xxi minus di xxi minus di2 1 578 6362 572003 5702 4 counted. Hollow circle 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 hollow. Testing of hypotheses I205s. No. She xxi minus di xxi minus di2 4 5 6 8 4 1 6 5 5 7 2 0 0 6 5 7 8 6 3 6 7 5 7 0 2 4 8 5 7 2 0 0 9 5 9 6 2 4 5 7 6 1 0 5 4 4 2 8 7 8 4 n equals 10 n area summation equals she 5720 n area summation minus equals xxi di2 1456. Therefore xxni equals n area summation equals 5720 10 5 72 kg and sigma s6xn equals n area summation minus equals di2 1 1456 10 1 1272 kg. Hence t equals minus 572 578 1272 10 1488 slash dot. Degree of freedom equals n1 equals 10 to 1 equals 9 as Ha is two-sided. We shall determine the rejection region applying two-tailed test at 5% level of significance, and it comes to as under, using table of t distribution for 9d. F. R. T greater than 2.262 is the observed value of t, i.e., 1.488 is in the acceptance region. We accept H0 at 5% level and conclude that the mean breaking strength of copper wires lot may be taken as 578 kg weight. The same inference can be drawn using Sandler's A statistic as shown below, Table 9.3, computations for A statistic S. No. She hypothesized mean dxiih equals minus micro 0 did 2 meters 578 kg. H0 equals 1 578 578 00 2 572 578 6363 570 578 8 644 568 578 10 100 asterisk table number 2 given in appendix at the end of the book. Con TD. Hollow circle 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 206 Research Methodology S. No 5 6 7 8 9 10 n equals 10 xi 578,570,572,596 hypothesized mean equals m 578 kh 0 578,578,578 grams. dxihdid2 equals minus micro 0.6085785785445786183 dn area summation equals minus I60d3606436324115 area summation equals 1816 therefore null hypothesis 22add2 equals n area summation equals minus equals iibgbg181660050044 0hh578 micro equals kilogram 0 alternate hypothesis Ha H does not equal micro 0.578 kilogram. As Ha is two-sided, the critical value of A statistic from the A statistic table number 10 given in appendix at the end of the book for N1 i.e., 10 to 1 equals 9d, F, at 5% level is 0.276. Computed value of A 0.5044 being greater than 0.276 shows that A statistic is insignificant in the given case and accordingly we accept H0 and conclude that the mean breaking strength of copper wire lot may be taken as 578 kg weight. Thus, the inference on the basis of T statistic stands verified by A statistic. Illustration 6. Raju restaurant near the railway station at Falna has been having average sales of 500 teacups per day. Because of the development of bus stand nearby, it expects to increase its sales. During the first 12 days after the start of the bus stand, the daily sales were as under: 550, 570, 490, 615, 505, 580, 570, 460, 600, 580, 530, 526. On the basis of this sample information, can one conclude that Raju restaurant's sales have increased? Use 5% level of significance. Solution. Taking the null hypothesis that sales average 500 teacups per day and they have not increased unless proved, we can write H0 micro equals 500 cups per day Ha micro greater than 500 as we want to conclude that sales have increased. As the sample size is small and the population standard deviation is not known, we shall use t-test assuming normal population and shall work out the test statistic T as Tx equals minus micro sigma Sn. To find x and sigma s we make the following computations smiley face. Testing of hypotheses I207 table 9.4s. No. She xxi minus di xxi minus di2 15502425702 224843490 583364 615 5505 43 1849 6580 32 1024 7570 22484 8460 887744 9 600 522704 10 580 32 1024 11530 183241252622484 n equals 10 n area summation equals she 6576 n area summation minus equals xxidi 223978 therefore xxni equals n area summation equals 657612548 and sigma s xxn equals n area summation minus equals di2 123978 1214668. Hence, T equals minus equals 548 500 4668 1248 1349 3558 /. Degree of freedom equals n1 equals 12 to 1 equals 11 as Ha is one-sided, we shall determine the rejection region applying one-tailed test in the right tail because Ha is of more than type at 5% level of significance and it comes to as under, using table of T distribution for 11 degrees of freedom, R. T greater than 1.796 the observed value of T is 3.558 which is in the rejection region and thus H0 is rejected at 5% level of significance and we can conclude that the sample data indicate that Raju restaurant's sales have increased. Hypothesis testing for differences between means in many decision situations, we may be interested in knowing whether the parameters of two populations are alike or different. For instance, we may be interested in testing whether female workers earn less than male workers for the same job. We shall explain now the technique of 208 research methodology hypothesis testing for differences between means. The null hypothesis for testing of difference between means is generally stated as H012 micro equals, where micro 1 is population mean of one population and micro 2 is population mean of the second population, assuming both the populations to be normal populations. Alternative hypothesis may be of not equal to or less than or greater than type as stated earlier and accordingly we shall determine the acceptance or rejection regions for testing the hypotheses. There may be different situations when we are examining the significance of difference between two means, but the following may be taken as the usual situations. 1. Population variances are known or the samples happen to be large samples. In this situation we use z-test for difference in means and work out the test statistic z as under. Zxx equals -1212 sigma sigma 22 pp plus nn12 in case sigma p1 and sigma p2 are not known. We use sigma s1 and sigma s2 respectively in their places, calculating 211 equals n area summation minus IDIDISXXN and 222 I sigma sigma minus equals S121 n area summation minus XXN1122. Samples happen to be large but presumed to have been drawn from the same population whose variance is known. In this situation we use z-test for difference in means and work out the test statistic z as under. Z equals -XX122 sigma F11 PIHG plus NN12 KJ. In case sigma p is not known, we use sigma S12. Combined standard deviation of the two samples in its place, calculating 2 sigma sigma 1 sigma EJ12 equals S122 SSNDNDNN plus 21212 where dxx equals -1112 didxx equals -2212 di22. Testing of hypotheses I209XNXNX1 12212 equals +NN1 3. Samples happen to be small samples and population variances not known but assumed to be equal. In this situation we use t-test for difference in means and work out the test statistic t as under. Txx12211 equals -n area summation minus plus n area summation minus plus minus times plus didi2ii22xxxxnnn2 111212 with d. F equals n1 plus n2 to 2. Alternatively, we can also state txx12 equals minus plus minus 212 bgbg sigma sigma 2 ss11121112 plus minus times plus 1212 with d. F equals n1 plus n2 to 2. Illustration 7. The mean produce of wheat of a sample of 100 fields in 200 pounds per acre with a standard deviation of 10 pounds. Another samples of 150 fields gives the mean of 220 pounds, with a standard deviation of 12 pounds. Can the two samples be considered to have been taken from the same population whose standard deviation is 11 pounds? Use 5% level of significance. Solution. Taking the null hypothesis that the means of two populations do not differ, we can write H0, micro equals 2HA, micro does not equal 1 2 and the given information is N1 equals 100, N2 equals 150, X by 200 pounds, equals 220 pounds, 1 2 1 OLBS, sigma equals 12 pounds, SS12 and KJ equals sigma P equals 11 pounds. Assuming the population to be normal, we can work out the test statistic Z as under. Z equals -XX12 sigma 2 F11 PHG plus NN1 2 200 220 minus I2 FBG I11 1100 1150 HG plus KJ. 210 Research methodology equals -20 142 1408. As Ha is two-sided, we shall apply a two-tailed test for determining the rejection regions at 5% level of significance which come to as under, using normal curve area table. R, Z greater than 1.96. The observed value of Z is 14.08 which falls in the rejection region and thus we reject H0 and conclude that the two samples cannot be considered to have been taken at 5% level of significance from the same population whose standard deviation is 11 pounds. This means that the difference between means of two samples is statistically significant and not due to sampling fluctuations. Illustration 8. A simple random sampling survey in respect of monthly earnings of semi-skilled workers in two cities gives the following statistical information. Table 9.5 City mean monthly standard deviation of size of earnings Rs. Sample data of sample monthly earnings Rs. A695, 40, 200 B710, 60175. Test the hypothesis at 5% level that there is no difference between monthly earnings of workers in the two cities. Solution. Taking the null hypothesis that there is no difference in earnings of workers in the two cities, we can write H0, micro 1 2 equals Ha. Micro 1 2 does not equal and the given information is sample 1, city A, sample 2, city B, x 1695 equals Rs x 2710 equals Rs sigma S140 equals Rs sigma S260 equals Rs N1 equals 200 N2 equals 175. As the sample size is large, we shall use z-test for difference in means assuming the populations to be normal and shall work out the test statistic z as under, zxxnnss equals minus plus 1221221 sigma sigma. Testing of hypotheses I to 11. Since the population variances are not known, we have used the sample variances, considering the sample variances as the estimates of population variances. Hence z equals minus plus equals minus plus equals minus 695, 710, 40, 200, 60, 175, 15, 82057, 2809, 2 BGBG. As Ha is two-sided, we shall apply a two-tailed test for determining the rejection regions at 5% level of significance which come to as under, using normal curve area table. R, z greater than 1.96. The observed value of z is 2.809 which falls in the rejection region and thus we reject H0 at 5% level and conclude that earning of workers in the two cities differ significantly. Illustration 9. Sample of sales in similar shops in two towns are taken for a new product with the following results. Town mean sales variance size of sample A 57.5.35 B 61.4.87. Is there any evidence of difference in sales in the two towns? Use 5% level of significance for testing this difference between the means of two samples. Solution. Taking the null hypothesis that the means of two populations do not differ, we can write H0 micro 1 2 equals Ha. Micro 1 2 does not equal and the given information as follows. Table 9.6 sample from town as sample 1 x 157 equals sigma S1253 equals N1 equals 210 research methodology equals minus 2014214008. Testing of hypotheses I to 11. Since the population variances are not known, we have used the sample variances, considering the sample variances as the estimates of population variances. Hence z equals minus plus equals minus plus equals minus 695, 710, 40, 200, 60, 175, 15, 82057, 2809, 2 BGBG. As Ha is two-sided, we shall apply a two-tailed test for determining the rejection regions at 5% level of significance which come to as under, using normal curve area table. R, z greater than 1.96. The observed value of z is 2.809 which falls in the rejection region and thus we reject H0 at 5% level and conclude that earning of workers in the two cities differ significantly. Illustration 9. Sample of sales in similar shops in two towns are taken for a new product with the following results. Town mean sales variance size of sample A 57.5.35 B 61.4.87. Is there any evidence of difference in sales in the two towns? Use 5% level of significance for testing this difference between the means of two samples. Solution. Taking the null hypothesis that the means of two populations do not differ, we can write H0 micro 1 2 equals Ha. Micro 1 2 does not equal and the given information as follows. Table 9.6 sample from town as sample 1 x 157 equals sigma S1253 equals N1 equals 5. Sample from town B is sample 2 x 261 equals sigma S2248 equals N2 equals 7. Since in the given question variances of the population are not known and the size of samples is small, we shall use t-test for difference in means, assuming the populations to be normal and can work out the test statistic t as under. Txxnnnnnnss equals minus plus times plus 1 2 1 2 2 2 1 2 1 2 1 1 2 1 1 1 2 BGBG sigma with d f equals n1 plus n2 to 2. 212 research methodology equals minus plus times plus equals minus 5761453648572151733053. BGBG degrees of freedom equals n1 plus n2 to 2 equals 5 plus 7 to 2 equals 10. As Ha is two-sided, we shall apply a two-tailed test for determining the rejection regions at 5% level which come to as under, using table of t distribution for 10 degrees of freedom. R, t greater than 2.228. The observed value of t is 3.053 which falls in the rejection region and thus, we reject H0 and conclude that the difference in sales in the two towns is significant at 5% level. Illustration 10. A group of 7-week-old chickens reared on a high-protein diet weigh 12, 15, 11, 16, 14, 14, and 16 ounces. A second group of 5 chickens, similarly treated except that they receive a low-protein diet, weigh 8, 10, 14, 10 and 13 ounces. Test at 5% level whether there is significant evidence that additional protein has increased the weight of the chickens. Use assumed mean, or A1 equals 10 for the sample of 7 and assumed mean, or A2 equals 8 for the sample of 5 chickens in your calculations. Solution. Taking the null hypothesis that additional protein has not increased the weight of the chickens, we can write H0, micro 1 2 equals ha, micro 1 2 greater than, as we want to conclude that additional protein has increased the weight of chickens since in the given question variances of the populations are not known and the size of samples is small. We shall use t-test for difference in means, assuming the populations to be normal and thus work out the test statistic t as under. Txxnnnnnnss equals minus plus times plus 1 2 1 2 2 2 1 2 1 2 1 1 2 1 1 1 2 bg sigma with d f equals n1 plus n2 to 2. From the sample data we work out xxs1221 sigma and sigma s22, taking high protein diet sample as sample 1 and low protein diet sample as sample 2, as shown below. Testing of hypotheses I213 table 9.7 sample 1 sample 2 S number x1i x1i a1 xai121 minus bgs no x2i x2i a2 xai222 minus bg a1 equals 10 a2 equals 8 1 1 2 2 4 1 8002 155252 102 43 11113 146364 166364 10245 144165 135256 144167 16636 n1 equals 7 n array summation minus equals xai1128 bg n array summation minus xai112 bg n2 equals 5 n array summation minus equals xai2215 bg n array summation minus xai222 bg equals 134 equals 69. Therefore xaxani1 111102871 equals plus n array summation minus equals plus equals bg ounces xaxani2 222281551 equals plus n array summation minus equals plus equals bg ounces sigma siixaxann1 211211211 equals minus sign n array summation minus bg equals minus equals 1342877136672 bg ounces sigma siixaxann 22222222221 equals minus sign n array summation minus bg equals minus equals 691555162 bg ounces. Hence T equals minus plus times plus 141171366751675217115 bg 214 Research methodology equals times equals 3 4 6 3 4 5 3 1 2 6 2 3 8 1 Degrees of freedom equals n1 plus n2 to 2 equals 10 as Ha is one-sided. We shall apply a one-tailed test in the right tail because Ha is of more than type for determining the rejection region at 5% level, which comes to as under. Using table of T distribution for 10 degrees of freedom. R. T greater than 1.812, the observed value of T is 2.381, which falls in the rejection region, and thus, we reject H0 and conclude that additional protein has increased the weight of chickens at 5% level of significance. Hypothesis testing for comparing two related samples. Paired t-test is a way to test for comparing two related samples, involving small values of n that does not require the variances of the two populations to be equal, but the assumption that the two populations are normal must continue to apply. For a paired t-test, it is necessary that the observations in the two samples be collected in the form of what is called matched pairs, i.e., each observation in the one sample must be paired with an observation in the other sample in such a manner that these observations are somehow matched or related, in an attempt to eliminate extraneous factors which are not of interest in test. 5. Such a test is generally considered appropriate in a before and after treatment study. For instance, we may test a group of certain students before and after training in order to know whether the training is effective, in which situation we may use paired t-test. To apply this test, we first work out the difference score for each matched pair, and then find out the average of such differences, d, along with the sample variance of the difference score. If the values from the two matched samples are denoted as xi and yi and the difference is by dt equals xi, yi, then the mean of the difference is i.e. ddni equals n Airy summation and the variance of the differences are sigma diff I ddnn. Di 2221 equals n Airy summation minus dot operator minus assuming the said differences to be normally distributed and independent, we can apply the paired t-test for judging the significance of mean of differences and work out the test statistic t as under. TDN diff equals minus 0 sigma with n1 degrees of freedom where d equals mean of differences 5 Donald L. Harnett and James L. Murphy, Introductory Statistical Analysis, p. 364. Testing of hypotheses I215 sigma diff equals standard deviation of differences n equals number of matched pairs. This calculated value of t is compared with its table value at a given level of significance as usual for testing purposes. We can also use Sandler's A-test for this very purpose as stated earlier in Chapter 8. Illustration 11. Memory capacity of 9 students was tested before and after training. State at 5% level of significance whether the training was effective from the following scores. Student 1 2 3 4 5 6 7 8 9 before 1 0 1 5 9 3 7 1 2 1 6 1 7 4 after 1 2 1 7 8 5 6 1 1 1 8 2 0 3. Use paired t-test as well as A-test for your answer. Solution. Take the score before training as x and the score after training as y and then taking the null hypothesis that the mean of difference is 0, we can write h0 micro 1 2 equals which is equivalent to test h0 laughing face equals 0 ha micro 1 2 less than. As we want to conclude that training has been effective as we are having matched pairs, we use paired t-test and work out the test statistic t as under. TDN diff equals minus 0 sigma. To find the value of t, we shall first have to work out the mean and standard deviation of differences as shown below. Table 9.8 Student score before score after difference training squared xi d equals xi yi d2 1 1 0 1 2 2 4 2 1 5 1 7 2 4 3 9 8 1 1 4 3 5 2 4 5 7 6 1 1 6 1 2 1 1 1 1 7 1 6 1 8 2 4 8 1 7 2 0 3 9 9 4 3 1 1 n equals 9 n Airy summation equals minus d7 n Airy summation equals d2 29. 216 Research methodology. Therefore mean of differences are ddni equals n Airy summation equals minus 7 9 0 7 7 8. And standard deviation of differences are sigma diff I ddnn equals n Airy summation minus dot operator minus 2 2 1 di equals minus times minus 2 9 7 7 8 9 9 1 2. Vg equals 2 9 4 4 1 7 1 5. Hence, t equals minus 0 7 7 8 0 1 7 1 5 9 7 7 8 0 5 7 2 1 3 6 1. /. Degrees of freedom equals n1 equals 9 to 1 equals 8. As ha is one-sided, we shall apply a one-tailed test in the left tail because ha is of less than type for determining the rejection region at 5% level which comes to as under, using the table of t distribution for 8 degrees of freedom. R, t less than 1.860 the observed value of t is minus 1.361 which is in the acceptance region and thus, we accept h0 and conclude that the difference in score before and after training is insignificant i.e., it is only due to sampling fluctuations. Hence we can infer that the training was not effective. Solution using A-test. Using A-test, we work out the test statistic for the given problem thus. ADDII equals n Airy summation equals minus 2 2 2 2 9 7 0 5 9 2 BG. Since ha in the given problem is one-sided, we shall apply one-tailed test. Accordingly, at 5% level of significance the table value of a statistic for n1 or 9 to 1 equals 8d. F, in the given case is 0.368 as per table of a statistic given in appendix. The computed value of a i.e., 0.592 is higher than this table value and as such a statistic is insignificant and accordingly h0 should be accepted. In other words, we should conclude that the training was not effective. This inference is just the same as drawn earlier using paired t-test. Illustration 12 The sales data of an item in 6 shops before and after a special promotional campaign are shops A B C D E F before the promotional campaign 532831 4850 42 after the campaign 582930 555645 Can the campaign be judged to be a success? Test at 5% level of significance. Use paired t-test as well as A-test. Testing of hypotheses I217 solution. Let the sales before campaign be represented as X and the sales after campaign as Y, and then taking the null hypothesis that campaign does not bring any improvement in sales, we can write H0 micro 1 2 equals, which is equivalent to test HD 0 equals ha micro 1 2 less than, as we want to conclude that campaign has been a success. Because of the matched pairs, we use paired t-test and work out the test statistic t as under TDN diff equals -0 sigma. To find the value of t, we first work out the mean and standard deviation of differences as under Table 9.9 shops sales before sales after difference campaign squared she d equals she ye d2a5358525b2829111 c313011 d48557449e50 56636 f424539 n equals 6 n Aries summation equals minus d21 n Aries summation equals d2121. Therefore ddni equals n Aries summation equals minus 21635 sigma diff iddnn equals n Aries summation minus dot operator minus equals minus times minus equals 222112135661308 dibg. Hence t equals minus equals minus 350 /. Degrees of freedom equals n1 equals 6 to 1 equals 5 as ha is one-sided. We shall apply a one-tailed test in the left tail because ha is of less than type for determining the rejection region at 5% level of significance, which come to as under, using table of t distribution for 5 degrees of freedom. R, t less than 2.015, the observed value of t is 2.784, which falls in the rejection region, and thus, we reject H0 at 5% level and conclude that sales promotional campaign has been a success. 218 Research methodology solution. Using a test. Using a test, we work out the test statistic for the given problem as under ADDII equals n Aries summation equals minus equals 2221212102744 bgbg. Since ha in the given problem is one-sided, we shall apply one-tailed test. Accordingly, at 5% level of significance, the table value of a statistic for n-1 or 6-1 equals 5d. F, in the given case, is 0.372 as per table of a statistic given in appendix. The computed value of a, being 0.2744, is less than this table value, and as such a statistic is significant. This means we should reject H0. Alternately, we should accept ha, and should infer that the sales promotional campaign has been a success. Hypothesis testing of proportions. In case of qualitative phenomena, we have data on the basis of presence or absence of an attributes. With such data, the sampling distribution may take the form of binomial probability distribution whose mean would be equal to np.operator and standard deviation equal to npq.operator, where p represents the probability of success, q represents the probability of failure, such that p plus q equals 1 and n, the size of the sample. Instead of taking mean number of successes and standard deviation of the number of successes, we may record the proportion of successes in each sample, in which case the mean and standard deviation, or the standard error, of the sampling distribution may be obtained as follows. Mean proportion of successes equals dot operator equals npbg, and standard deviation of the proportion of successes equals dot operator pqn. In n is large, the binomial distribution tends to become normal distribution, and as such, for proportion testing purposes, we make use of the test statistic z as under zppqn equals minus dot operator dollar, where $p is the sample proportion. For testing of proportion, we formulate H0 and ha and construct rejection region, presuming normal approximation of the binomial distribution, for a predetermined level of significance, and then may judge the significance of the observed sample result. The following examples make all this quite clear. Illustration 13. A sample survey indicates that out of 3,232 births, 1,705 were boys and the rest were girls. Do these figures confirm the hypothesis that the sex ratio is 50-50? Test at 5% level of significance. Solution. Starting from the null hypothesis that the sex ratio is 50-50, we may write testing of hypotheses I219 HPPH0012 equals HPPAH does not equal 0, hence the probability of boy birth or p equals 1-2, and the probability of girl birth is also 1-2. Considering boy birth as success and the girl birth as failure, we can write as under the proportion success or p equals 1-2, the proportion of failure or q equals 1-2, and n equals 3,232 given. The standard error of proportion of success equals dot operator equals times equals PQN 1,2,1,2,3,2,3,2,0,0,0,88. Observed sample proportion of success, or $P equals 1705323205275 and the test statistic ZPPPQN equals minus dot operator equals minus equals $05275 5000 0088 3125 is Ha is two-sided in the given question. We shall be applying the two-tailed test for determining the rejection regions at 5% level which come to as under, using normal curve area table, R. Z greater than 1.96. The observed value of Z is 3.125 which comes in the rejection region since R. Z greater than 1.96 and thus, H0 is rejected in favor of Ha. Accordingly, we conclude that the given figures do not conform the hypothesis of sex ratio being 50-50. Illustration 14. The null hypothesis is that 20% of the passengers go in first class, but management recognizes the possibility that this percentage could be more or less. A random sample of 400 passengers includes 70 passengers holding first-class tickets. Can the null hypothesis be rejected at 10% level of significance? Solution. The null hypothesis is H0, P equals 20% or 0.20 and Ha, P does not equal 20%. 220 Research methodology hints, P equals 0.20 and Q equals 0.80. Observed sample proportion $PBG equals 74 hundredths equals 0.175 and the test statistic ZPPPQN equals minus dot operator equals minus times equals minus $0.175202080 400 125 is Ha is two-sided. We shall determine the rejection regions applying two-tailed test at 10% level which come to as under, using normal curve area table. R. Z greater than 1.645. The observed value of Z is minus 1.25 which is in the acceptance region and as such H0 is accepted. Thus the null hypothesis cannot be rejected at 10% level of significance. Illustration 15. A certain process produces 10% defective articles. A supplier of new raw material claims that the use of his material would reduce the proportion of defectives. A random sample of 400 units using this new material was taken out of which 34 were defective units. Can the supplier's claim be accepted? Test at 1% level of significance. Solution. The null hypothesis can be written as H0, P equals 10% or 0.10 and the alternative hypothesis Ha, P less than 0.10 because the supplier claims that new material will reduce proportion of defectives. Hence, P equals 0.10 and Q equals 0.90. Observed sample proportion $P equals 34 400ths equals 0.085 and test statistic ZPPPQN equals minus dot operator equals minus times equals minus $0.85101090 400 015 015 100 as Ha is one-sided. We shall determine the rejection region applying one-tailed test in the left tail because Ha is of less than type at 1% level of significance and it comes to as under, using normal curve area table. R. Z less than 2.32 is the computed value of Z does not fall in the rejection region. H0 is accepted at 1% level of significance and we can conclude that on the basis of sample information, the supplier's claim cannot be accepted at 1% level. Hypothesis testing for difference between proportions. If two samples are drawn from different populations, one may be interested in knowing whether the difference between the proportion of successes is significant or not. In such a case, we start with the hypothesis that the difference between the proportion of success in sample $P1BG and the proportion testing of hypotheses I-221 of success in sample $P2BG is due to fluctuations of random sampling. In other words, we take the null hypothesis as HPP, $012 equals and for testing the significance of difference, we work out the test statistic as under. Z12 equals minus dot operator plus dot operator $$$$$$$$1 PPPQN221 where $P1 equals proportion of success in sample $P2 equals proportion of success in sample $$$ equals minus QP111 equals minus $QP122N1 equals size of sample 1 N2 equals size of sample 2 and $PQN111 PQN22 PQN2 plus equals the standard error of difference between two sample proportions. Asterisk 2 Then, we construct the rejection regions depending upon the Ha for a given level of significance and on its basis we judge the significance of the sample result for accepting or rejecting H0. We can now illustrate all this by examples. Illustration 6. A drug research experimental unit is testing two drugs newly developed to reduce blood pressure levels. The drugs are administered to two different sets of animals. In Group 1, 350 of 600 animals tested respond to drug 1, and in Group 2, 260 of 500 animals tested respond to drug 2. The research unit wants to test whether there is a difference between the efficacy of the said two drugs at 5% level of significance. How will you deal with this problem? This formula is used when samples are drawn from two heterogeneous populations where we cannot have the best estimate of the common value of the proportion of the attribute in the population from the given sample information. But on the assumption that the populations are similar as regards the given attribute, we make use of the following formula for working out the standard error of difference between proportions of the two samples. SE diff pp. 1 2 minus equals dot operator plus dot operator PQN001 where P11220 equals dot operator plus dot operator NPNPN equals $$ equals best estimate of proportion in the population plus 1 2 equals minus QP100. 222 Research Methodology Solution. We take the null hypothesis that there is no difference between the two drugs, i.e., HPPO 2 $$ equals the alternative hypothesis can be taken as that there is a difference between the drugs, i.e., HPPA $1 $2 does not equal, and the given information can be stated as $P1350600 equals $$ QP1110417 equals minus equals N1 equals $600 per P2 260,500 equals $$ QP2 210480 equals minus equals N2 equals 500. We can work out the test statistic Z thus. ZPPPQNPQN equals minus plus $$ 1211122205830520520 583417600 580 BG equals 2.093 as Ha is two-sided. We shall determine the rejection regions applying two-tailed test at 5% level, which comes as under using normal curve area table. R Z greater than 1.96. The observed value of Z is 2.093, which is in the rejection region, and thus, H0 is rejected in favor of Ha, and as such we conclude that the difference between the efficacy of the two drugs is significant. Illustration 17. At a certain date in a large city, 400 out of a random sample of 500 men were found to be smokers. After the tax on tobacco had been heavily increased, another random sample of 600 men in the same city included 400 smokers. Was the observed decrease in the proportion of smokers significant? Test at 5% level of significance. Solution. We start with the null hypothesis that the proportion of smokers even after the heavy tax on tobacco remains unchanged, i.e. HPPO 2 $$ equals, and the alternative hypothesis that proportion of smokers after tax has decreased, i.e. HPPA $1 $2 greater than. On the presumption that the given populations are similar as regards the given attribute, we work out the best estimate of proportion of smokers P0 in the population as under, using the given information. PNPNPNNO 1 1 2 2 1 2 500 400 500 600 400 600 500 600 800 1 100 811 7273 equals plus equals FHGIKJ plus FHGIKJ plus equals $. Testing of hypotheses I223. Thus, Q0 equals 1, P0 equals 0.2727. The test statistic Z can be worked out as under. ZPPPQNPQN equals minus plus $. 1 2001002 400 500 400 600 7273 2727 500 7273 2727 600 BG equals 0133 0027 4926. As the Ha is one-sided, we shall determine the rejection region applying one-tailed test in the right tail because Ha is of greater than type at 5% level, and the same works out to as under, using normal curve area table. R Z greater than 1.645. The observed value of Z is 4.926, which is in the rejection region, and so we reject H0 in favor of Ha and conclude that the proportion of smokers after tax has decreased significantly. Testing the difference between proportion based on the sample and the proportion given for the whole population. In such a situation we work out the standard error of difference between proportion of persons possessing an attribute in a sample and the proportion given for the population as under. Standard error of difference between sample proportion and population proportion, or SE diff PPPQNNNN. minus equals dot operator minus where P equals population proportion Q equals 1 P N equals number of items in the sample N equals number of items in population and the test statistic Z can be worked out as under. ZPPPQNNNN equals minus dot operator minus dollar. All other steps remain the same as explained above in the context of testing of proportions. We take an example to illustrate the same. Illustration 18. There are 100 students in a university college, and in the whole university, inclusive of this college, the number of students is 2,000. In a random sample study 20 were found smokers in the college and the proportion of smokers in the university is 0.05. Is there a significant difference between the proportion of smokers in the college and university? Test at 5% level. 224 Research methodology solution. Let HPP 0. Equals there is no difference between sample proportion and population proportion, and HPPA. Does not equal there is difference between the two proportions, and on the basis of the given information, the test statistic Z can be worked out as under. Minus Z equals minus PP dot operator minus equals PQNNNN. 20 100 05 05 95 2000 100 minus BG 100 2000 0150 equals 0021 7143. As the HA is two-sided, we shall determine the rejection regions applying two-tailed test at 5% level, and the same works out to as under, using normal curve area table. R, Z greater than 1.96. The observed value of Z is 7.143, which is in the rejection region, and as such we reject H0 and conclude that there is a significant difference between the proportion of smokers in the college and university. Hypothesis testing for comparing a variance to some hypothesized population variance. The test we use for comparing a sample variance to some theoretical or hypothesized variance of population is different than Z-test or the t-test. The test we use for this purpose is known as chi-square test, and the test statistic symbolized as chi2, known as the chi-square value, is worked out. The chi-square value to test the null hypothesis viz. H2 sigma SP equals worked out as under 2 chi2 sigma S equals minus 2 NBG 1P, where sigma S2 equals variance of the sample, sigma P2 equals variance of the population, N1 equals degree of freedom, N being the number of items in the sample. Then by comparing the calculated value of chi2 with its table value for N1 degrees of freedom at a given level of significance, we may either accept H0 or reject it. If the calculated value of chi2 is equal to or less than the table value, the null hypothesis is accepted, otherwise the null hypothesis is rejected. This test is based on chi-square distribution, which is not symmetrical in all. Testing of hypotheses I-225. The values happen to be positive. One must simply know the degrees of freedom for using such a distribution. Testing the equality of variances of two normal populations. When we want to test the equality of variances of two normal populations, we make use of F-test based on F distribution. In such a situation, the null hypothesis happens to be H2220 equals sigma PPP121 and sigma P22 representing the variances of two normal populations. This hypothesis is tested on the basis of sample data, and the test statistic F is found, using sigma S12 and sigma S22, the sample estimates for sigma P12 and sigma P22 respectively, as stated below, 2 where DI equals N Aries summation minus IF equals sigma S1 sigma 2 S2222112222 ISXXN and sigma minus equals BGDIS121 N Aries summation minus XXN BG112. While calculating F, sigma S12 is treated greater than sigma S22, which means that the numerator is always the greater variance. Tables for F distribution have been prepared by statisticians for different values of F at different levels of significance for different degrees of freedom for the greater and the smaller variances. By comparing the observed value of F with the corresponding table value, we can infer whether the difference between the variances of samples could have arisen due to sampling fluctuations. If the calculated value of F is greater than table value of F at a certain level of significance for N1 to 1 and N2 to 2 degrees of freedom, we regard the F ratio as significant. Degrees of freedom for greater variance is represented as version 1 and for smaller variance as version 2. On the other hand, if the calculated value of F is smaller than its table value, we conclude that F ratio is not significant. If F ratio is considered non-significant, we accept the null hypothesis, but if F ratio is considered significant, we then reject H0, i.e., we accept HA. When we use the F test, we presume that I, the populations are normal, E, samples have been drawn randomly, E, observations are independent, and IV, there is no measurement error. The object of F-test is to test the hypothesis whether the two samples are from the same normal population with equal variance or from two normal populations with equal variances. F-test was initially used to verify the hypothesis of equality between two variances, but is now mostly used in the C Chapter 10 entitled chi-square test for details. F distribution tables Table 4a and Table 4b have been given in appendix at the end of the book. 226 Research methodology context of analysis of variance. The following examples illustrate the use of F-test for testing the equality of variances of two normal populations. Illustration 19. Two random samples drawn from two normal populations are sample 120, 1626, 27, 23, 22, 18, 24, 25, 19, sample 2, 27, 33, 42, 35, 32, 34, 38, 28, 41, 43, 30, 37. Test using variance ratio at 5% and 1% level of significance whether the two populations have the same variances. Solution. We take the null hypothesis that the two populations from where the samples have been drawn have the same variances, i.e., HPPO 2, 2, 1, 2. Sigma equals. From the sample data we work out sigma S12 and sigma S22 as under. Table 9.10 Sample 1 Sample 2 x1 ixxi11 minus dixxi112 minus dix2 ixxi22 minus dixxi222 minus di20 2 4 2 7 8 6 4 1 6 6 3 6 3 3 2 4 2 6 4 1 6 4 2 7 4 9 2 7 5 2 5 3 5 0 0 2 3 1 1 3 2 3 9 2 2 0 0 3 4 1 1 1 8 4 1 6 3 8 3 9 2 4 2 4 2 8 7 4 9 2 5 3 9 4 1 6 3 6 1 9 3 9 4 3 8 6 4 3 0 5 2 5 3 7 2 4 n area summation equals she 1220 n area summation minus equals xxi 1 1 2 1 2 0 di n area summation equals xi 2 4 2 0 n area summation minus equals xxi 2 2 2 3 1 4 di n 1 equals 1 0 n 2 equals 1 2 xxn xxn ii 1 1 1 2 2 2 2 2 0 1 0 2 2 4 2 0 1 2 3 5 equals n area summation equals n area summation equals. Therefore sigma sxn 1 2 1 1 2 1 1 1 2 0 1 0 1 1 3 3 3 equals n area summation minus equals di. Testing of hypotheses I227 and sigma SIXXN2 2 2 2 2 2 1 3 1 4 1 2 1 2 8 5 5 equals n area summation minus equals di. Hence, FSSSS equals greater than sigma 2 1 2 1 2 2 2 2 kj equals 2855 1333 214. Degrees of freedom in sample 1 equals n1 to 1 equals 10 to 1 equals 9 degrees of freedom in sample 2 equals n2 to 1 equals 12 to 1 equals 11 as the variance of sample 2 is greater variance, hence version 1 equals 11. V2 equals 9. The table value of F at 5% level of significance for version 1 equals 11 and version 2 equals 9 is 3.11 and the table value of F at 1% level of significance for version 1 equals 11 and version 2 equals 9 is 5.20. Since the calculated value of F equals 2.14 which is less than 3.11 and also less than 5.20, the F ratio is insignificant at 5% as well as at 1% level of significance and as such we accept the null hypothesis and conclude that samples have been drawn from two populations having the same variances. Illustration 20 given n1 equals 9, n2 equals 8 n area summation minus equals xxi1 1 2 1 8 4 di n area summation minus equals xxi2 2 2 3 8 di. Apply F test to judge whether this difference is significant at 5% level. Solution. We start with the hypothesis that the difference is not significant and hence, HPPO 2 2 1 2, sigma equals. To test this, we work out the F ratio as under. FXXNXXNSSII equals n area summation minus n area summation minus sigma 1 2 2 2 1 1 2 1 2 2 2 2 1 1 dibg equals 1848 387 23 543 425 V1 equals 8 being the number of D. F. For greater variance version 2 equals 7 being the number of D. F. For smaller variance. 228 Research methodology. The table value of F at 5% level for version 1 equals 8 and version 2 equals 7 is 3.73. Since the calculated value of F is greater than the table value, the F ratio is significant at 5% level. Accordingly we reject H0 and conclude that the difference is significant. Hypothesis testing of correlation coefficients. We may be interested in knowing whether the correlation coefficient that we calculate on the basis of sample data is indicative of significant correlation. For this purpose we may use, in the context of small samples, normally either the t-test or the f-test depending upon the type of correlation coefficient. We use the following tests for the purpose. A. In case of simple correlation coefficient, we use t-test and calculate the test statistic as under, trn equals -yx minus ryx. 212 with n2 degrees of freedom ryx being coefficient of simple correlation between x and y. This calculated value of t is then compared with its table value, and if the calculated value is less than the table value, we accept the null hypothesis at the given level of significance and may infer that there is no relationship of statistical significance between the two variables. B. In case of partial correlation coefficient, we use t-test and calculate the test statistic as under, equals minus trn kpbg12 minus rp with n, k degrees of freedom, n being the number of paired observations and k being the number of variables involved. Rp happens to be the coefficient of partial correlation. If the value of t in the table is greater than the calculated value, we may accept null hypothesis and infer that there is no correlation. C. In case of multiple correlation coefficient, we use f-test and work out the test statistic as under, 2f1 equals minus bg1 rkrnk2 ejbg minus minus. Where r is any multiple coefficient of correlation, k being the number of variables involved and n being the number of paired observations. The test is performed by entering tables of the f distribution with version 1 equals k1 equals degrees of freedom for variance in numerator, v2 equals n, k equals degrees of freedom for variance in denominator. If the calculated value of f is less than the table value, then we may infer that there is no statistical evidence of significant correlation. Only the outline of testing procedure has been given here. Readers may look into standard tests for further details. Testing of hypotheses. I-229 limitations of the tests of hypotheses. We have described above some important tests often used for testing hypotheses on the basis of which important decisions may be based. But there are several limitations of the said tests which should always be borne in mind by a researcher. Important limitations are as follows. The tests should not be used in a mechanical fashion. It should be kept in view that testing is not decision-making itself, the tests are only useful aids for decision-making. Hence, proper interpretation of statistical evidence is important to intelligent decisions. 6. Tests do not explain the reasons as to why does the difference exist, say between the means of the two samples. They simply indicate whether the difference is due to fluctuations of sampling or because of other reasons, but the tests do not tell us as to which are the other reasons causing the difference. Results of significance. Tests are based on probabilities and as such cannot be expressed with full certainty. When a test shows that a difference is statistically significant, then it simply suggests that the difference is probably not due to chance. Statistical inferences based on the significance tests cannot be said to be entirely correct evidences concerning the truth of the hypotheses. This is especially so in case of small samples where the probability of drawing erring inferences happens to be generally higher. For greater reliability, the size of samples be sufficiently enlarged. All these limitations suggest that in problems of statistical significance, the inference techniques or the tests must be combined with adequate knowledge of the subject matter along with the ability of good judgment. Question.